Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's newsletter, well, we're going to take a look at a little MSA case study that I've been sent. I've been sent a question, some measurement system analysis data. It's just a good opportunity to learn a practical example of MSA, something that's just a little bit different, and it shows that sometimes MSA, the results can be bad, but actually that doesn't mean that your measurement system can't be used. Before we do that though, I just want to remind you that I've now set up a little donate page. So if you like this advice that I leave and you want to donate, just at the bottom you can buy me a coffee. I've also left links to other measurement system analysis videos. So there's about 3 or 4 links below, so you can look at several videos now and look at the MSA subject in a totality. If you'd like to know more, it's covered in my book, Drink Tea and Read the Paper. There's also a link below for the electronic version of this, so you don't have to pay the full price now. There's now an electronic version for just a few pounds. So we're going to take a look at this MSA case study. But if you'd like to click on any of those links, please do so. That helps with the channel as well. Thank you very much. So we're going to take a look at an MSA case study. And just a little reminder, 3 questions. 3 questions your MSA is trying to answer. Is my system any good? 2, where is the problem? 3, what am I going to do about it? So there's the 3 questions that we need to answer. Let's take a look at the data that I've been sent. So just to set this up, the company concerned seems to be measuring the revs per minute of a piece of machinery. So it's important that they get the revs under control. So they've bought a piece of equipment to measure the revs, and then the sensible thing they're doing is saying, well, let's do an MSA. Let's make sure that this thing works. Let's make sure that the method isn't spoiling a really technical and well-made piece of equipment. So we are measuring revs per minute. Let's take a look at the data. So here we are, is the MSA data template as it's set up in DOE Pro. You can see that we've got 2 operators. We've got 2 operators and they've done two measurements each, which is great. The first thing that strikes me about looking at this MSA is I get the sense that this is the same revs per minute. So each one of these is the same setting of the machine. So in other words, if the measurement system worked perfectly, what you would get here is 40 data points all sitting in exactly the same place with no variability. Now straight away, that's a learning point, because what you should have done is you should have given the measurement system several speeds to look at, because what we've done here is we've made sure that there is no variability in the measurements. There's no variability in the parts. Normally you would be measuring parts, but we've made sure that there's no variability in the parts. And because there's no variability in the parts, of course the maths is going to say, well, all the variability is in the measurement system, which is exactly what the results actually tell us. So that's the first thing. These results, these measurements should have been on different speeds, not on the same speed. So let's take a look at what the MSA says. And there we go, look. There's the MSA agreeing with that. It says 100% of all the variability is measurement error, which is absolutely correct because there was no difference in the item that you were measuring. So the MSA has worked brilliantly well. And then what the software has said, look, and the calculations said, well, look, 30% of your tolerance is getting used up by the measurement error. And there's the tolerance up above. Now, in theory, in answer to our first question, is my measurement system any good? The answer would be no, because that doesn't meet up to our guideline reference of we want this to be at 0.1, which is the equivalent of just 10% of my tolerance is used up by measurement error. But in this instance, this measurement system is okay. And we're going to have a look at some other diagrams to just make the point. So if I keep going down, these are the averages. Now you can see here that normally this wouldn't be an acceptable result, because what you want to see the two lines as close to one another as possible, and you also want to see them follow a similar pattern. What we have here, look, is one operator thinks the result is getting faster, one operator thinks the result is getting slower. So that's not great. So that does need tidying up, that does need improving. So from the point of view, is my measurement system any good? No. What sort of problems am I getting? Well, clearly I'm not getting reproducibility here. And what am I going to do about it? Well, you'll see later on that one of the operators, operator 2, is much more variable, and that's where the work needs to be done in developing a standard operating procedure for operator 2. But let's keep going. Why is this measurement system still okay? Well, this is the reason here. If you think this blue distribution in the middle, these are the measurements, the capability, the variability coming from all the measurements that you had. Now what you actually had was 40 points that were all in the same place. I think it's 48 points actually in the case of this MSA. 48 points all in the same place. And of course what you're trying to do is you're trying to set the machine in a particular place. And the question is, does the measurement system allow you to set the machine? Does the measurement system allow you to see if you're in the tolerance band or not? So if you look at this, if you set this machine up here and the machine started to misbehave and started to walk to the left or walk to the right, these are the tolerances, by the way, here. This is the lower spec, this is the upper spec. If this setting started to walk to the left or to the right towards these tolerances outside the acceptable band, would your measurement system see it? Well, yes. If you started getting results here, this thing would spot that. So this is okay. This will enable you to put this distribution, if you wanted to put this distribution on the middle here, it would enable you to do that. It would also enable you to control the process and keep it well away from the acceptable tolerances. So this measurement system is perfectly capable of doing the task you asked it to do. So this is the difference between the two rules. Is my measurement system any good? Normally you would pass the two rules, precision to tolerance, precision to total. Both of them you want to be down at the 0.1 level. That would be the basic MSA rule. But in this case, this is perfectly capable of doing the practical job you asked it to do. So it's not passing the theoretical rules, but it's passing the practical rules. Now if we look at this as a CPK value rather than this misclassification diagram here from the software, I've now put it as a CPK diagram just to make the point. Look, you've got fantastic CPK. Is this measurement system capable of holding you in this band here? Yes, it is. Would it notice if you started to wander over here? Yes, it would. Therefore, it's perfectly capable of controlling the process, and that's what it's designed to do. So it's not going to misclassify. It's not going to tell you you've got good settings when you've got bad settings, or vice versa. It's perfectly capable of controlling the process in a region that you're interested. So actually, the measurement system is perfectly good enough for the task you're asking it to do. One last thing, does it need improving? Well, yes, it does. And we already mentioned, look, well, operator 1 has clearly got some method here. This guy, he clearly knows what he's doing. I mean, this is a new piece of equipment, I'm guessing. He clearly has a method that works and is pretty repeatable to within a few numbers of one another. This person, on the other hand, well, it's not the worst result in the world, being 20 out in this case, but you can clearly see that person, whatever it is they're doing, they're just not up to the task. So if we can get a standard operating procedure from this person here and then train it to this person here, that is the minimum you would do. But actually, this measurement system is perfectly okay for the practical job you're asking it to do. Okay, so there was the case study, MSA. The 3 questions, normally we'd answer them with the statistics, but the question I was answering up here is practically, it was a practical thing. Can he practically do the job? And if the answer is yes, then actually the rest of the statistics, they don't really matter. And what this relates to is, do you have a good CPK? So if you have a measurement system, if you have a capability, first thing you should always do is a CPK. So if you do a CPK and it looks brilliant, but then you do the MSA and it's terrible, so you've got lots of error here, people tend to panic and go, well, I've got a very poor measurement system. Doesn't matter. You've got a great CPK. Your measurement system's not going to influence the situation at all. So it doesn't matter. So you've got to use MSA in the right context. If I got this terrible CPK, and when I did the MSA, most of it was measurement error. Well, now the measurement system is crucially important to you solving that problem. You don't have a problem here. Why would you start one? So use your MSA properly. If you don't have a problem, you don't need to worry about it. If you do have a problem, it's a huge component of solving the problem. MSA case study, use it correctly. Don't cause yourself any unnecessary problems. Mark, I hope that answers your question that you posed to me yesterday. And as I say, if people would like to donate, they like this advice, then please just click on the link below. Thank you very much.